Hello everybody. Today we will be talking about creating problems for competitive programming contests and also about testing them and testing our programs during the contest when we are participants. So first a bit about inventing problems, because this is the first step of creating a problem. There are a lot of ways, there are a lot of sources from which you can get some ideas. For example, you can play a computer game and invent something from it. For example, you play some strategic game, you see that there are some buildings that have some cost, and once you build them, you will get more income. So maybe it makes sense. Even during the game, you might think whether it's optimal now to build this building. And maybe it can be made as a problem, where you're given a list of buildings or a list of some upgrades, and you should choose the optimal order of buying them to get some amount of money as soon as possible. Also, there can be some games when you're a hero and you slay monsters or something. You have some health points, some attack. Maybe you can also use some skills or special powers. Maybe you can, for example, if monsters are in some points of the grid, maybe you can use a fireball and kill monsters in some circle. Or do something with that. Or you're standing in some place, and when you cast that fireball, first it flies in some direction, so it will kill monsters inside some circle, but there should be no obstacle between you and that circle. And for example, this is what I invented like 5 seconds ago. So you can just think about some idea and can, even without thinking about it as a problem for a contest, you can think, what makes sense here? What makes sense in the story? Because this is how you can get many reasonable ideas that indeed fit the story. And then you must just check whether some of them can be a problem. Being good in competitive programming helps a lot, because once you have this problem, this idea, you should first estimate whether it's likely solvable. And even if it's solvable, whether it will be cool. Okay. There, for example, many problems are NP-hard. Usually when I invent a problem, I don't think whether it's NP-hard or not. I just think what observations I have here, because even if this problem isn't solvable in polynomial time, there are two cases. Either it's reasonable to give it with very small constraints and require not polynomial solution, because maybe this version is interesting anyway. And the other possibility, a very good thing, is that you don't have to choose this exact problem, because even if you find some observations, if you find some solution that maybe has one flaw, you can't make one step faster than in polynomial time, maybe you can adjust the statement. Maybe you can change something in the problem to make your solution work, to make your observation allowing you to solve a problem. So there are some real life ideas, like slaying monsters with fireball. And there are also some ideas related to just numbers. You are given a sequence of numbers, and let's do something with that. Count the number of subsets that have sum not exceeding some given x. Find the number of intervals that satisfy some condition. For example, the sum of numbers, if the length is L, the sum of numbers must be at least L times length of segment times some x from the input. For example, this problem, I didn't invent it now. This is a very well-known problem with some existing solution, so it indeed makes sense. It's possible to solve it in linear times logarithm complexity, but we couldn't use it now because it's well-known. So it's a problem, it's some issue, like today, in this year and in the next years, that many problems were already used. And nobody knows all the problems, but we can see an idea and then estimate how likely it is to be known. For example, count the number of subsets with sum not exceeding x. For me, it's obvious that it already appeared in many contests, because it's short idea. Idea is simple. Not necessarily solution is simple, but idea is very simple, so it's likely that someone already did that. Of course, sometimes there are short ideas that are surprising or unusual. So then, maybe even if idea is short, maybe problem is new. And you can just guess, and once you propose a problem to some contest, someone with more experience will, there is usually some coordinator or tester. At least one person working on a problem should be quite experienced, for example, especially in setting problems, but it also means he has some experience in estimating whether problem is well known, even if he doesn't know it. And there are many problems that you can invent based on algorithms that you know. For example, there are many algorithms on trees, so you can just say that I will do something with tree. So, and given a tree, maybe you think that you know centroids very well, so maybe you will invent some new problem that will use centroids. So maybe you can start with solution and then just build the whole problem based on solution only, or an idea for a solution. So centroids allow us to do something, to do some queries. Some more complicated centroids allow us to do some queries. So maybe we will have a tree and we will make some queries on that tree. For example, for given vertex and some radius, for example, 1, for all vertices that are within distance at most 1, so for all neighbors, we change their value, or we add some value to them, to those vertices. And there will be query, find the value of some vertex, or find the value of the sum of values in some subtree. Those are kinds of problems where you know many problems already, you know some algorithms used in competitive programming, and you're trying to make a problem using those. Usually those kind of problems have less quality, smaller quality, because they are kind of similar to other problems, but it doesn't mean that you shouldn't do it this way. Many great problems are created this way, and it might be the easier way, and one must start from something. So it's also a good thing. Another way of creating problems is to make something constructive, require something constructive. So there are a lot of problems that have statement, construct something, for example, tree, or a polygon that satisfies some condition. For example, construct a substring that will have exactly some number of substrings of length 3 that will have all characters distinct. This is also an idea that I invented 5 seconds ago. Okay? So you are given, in the input you are given n, length of string, you are given k, up to n minus 2, I think, and let's say you are allowed to use characters, lowercase English characters. Construct a string of length n that there is exactly k substrings of length 3 that have all 3 characters distinct. I think it would be quite easy problem. But you can also say, construct a polygon that have some number of vertices and have some area, have some area and some diameter, the distance between two farthest vertices. Or for given something, then from constructive problems, it's quite easy to some optimal problems. So I proposed this problem moments ago, but we can turn it from constructive into something possibly harder. It's also a construct, kind of. But we can say, find the smallest, lexicographically smallest string that satisfies that condition. And now it would be a problem that I think I would use in my contest. There are many problems I can invent, and some of them are boring, some of them are too similar to other problems, but I don't, right now from my perspective, I don't remember a problem similar to this one. There are a lot of problems, find smallest lexicographically string or sequence, so it makes this problem not so cool with that smallest lexicographically thing, but it's something. I think there is an easy solution, and I think it would make a good easy problem. Of course, right now I can't anymore use this problem, but I can invent a lot of easy problems, so it isn't that bad for me to tell you this idea. Okay, so now it's a wasted problem, but it shows you what can be a good idea and how can you create that. So here I started from thinking, maybe there will be some constructive problem, and then I added one more thing, find lexicographically smallest solution. Now I have a reasonable problem. One more way to invent a problem is to take old problem, possibly yours, maybe not, and increase constraints. Just increasing constraints is usually bad because maybe someone already solved that problem and thought about harder solution. But often you can also change a problem a bit, make it harder not only by increasing constraints, but for example by removing some constraint. Constraint, it's guaranteed that there will be exactly one solution, whatever. Or you can say that we have one more type of queries. So now, previously the intended solution was offline, but now we change some numbers during the process. And it's usually the best. It usually works the best when the problem you took is easy, was already easy, trivial, that kind of thing, because then usually by making it harder, you indeed make a completely new problem. Because if problem was already medium difficulty, then usually by making it harder, you change it only a little. So then it's possible that someone already, when was solving that problem, already thought about that exact thing. So I was talking about computer games, but you can also take some board game you like. You can make some chess problem. For example, there are many problems with doing something with queens or towers, putting them in a grid and counting something. Those are usually math problems, but if you like math, then of course you should try to invent some math problem. You can also take some board game. For example, we played Avalon yesterday, and we can make a problem kind of like the following one. The statement describes a game, and let's say there are B bad guys and J good guys, G good guys, And in the set of players, bad guys know each other. It's like in Mafia game also. Bad guys know each other, and during the game, you are observing the game, and you know that some players accused some other players, were suspicious about someone else. So you are given a set of edges in the graph. So you are given a set of pairs, A, B. It means that player A doesn't like player B or something, that he doesn't trust him. And you can say in the statement whatever fits that board game, that for example, it's guaranteed that if someone doesn't trust the other, then it's impossible that they are both bad guys or something. Okay? You can adjust the exact statement as long as it's reasonable. Like for example, it's stupid to now say something that doesn't really match the rules of the game. So you should be reasonable, but if you think then about a solution and you find some solution that would work for some version of the statement, just make that version of the statement. And you can use as many rules from the board game as you want. For example, in that Avalon game, there's also one special good guy. So good guys don't know each other, then they don't know anything, so they can usually accuse anyone. But there is one special good guy. He's called Merlin in that game, and that guy knows everything. And but on the other hand, his difference from other good guys, he knows everything, but his difference from bad guys is that bad guys don't know Merlin. Why don't they know each other? So maybe it's also said that there must be one good guy that didn't accuse any other good person. And maybe he's active, and maybe it's guaranteed that he accused at least one bad guy. And from that you, for example, you're given the list of edges in the input, and the statement says, find at least one possibility of saying who are bad, who are good, or say how many ways are there, or say just yes or no. I think that this problem, I didn't think about this problem longer than 10 seconds, so I don't know whether there is a polynomial solution. Maybe. It looks like some graph problem. So there is, of course, 2 power n, when n is the number of players, exponential solution that checks all possibilities. But maybe it's solvable faster. So there are some puzzles. There are some known puzzles. For example, there are three people sitting in a row. Each of them has a hat, black or white, and so each person knows only colors of hats before him. They also have some extra information. For example, even number of you wears black hats or something. And in some order they say, I don't know what hat I have, I don't know. And finally the guy who didn't see anything, he says, I know that I have black hat. Something like that. And maybe you can think about that puzzle, and you can make it more general, maybe with n players, and maybe it will be a problem. And such a problem, it won't require some standard solution, like flows, dynamic programming. Maybe it will be dynamic programming, but it won't be usual. But a problem in competitive programming can also be cool, even if it doesn't use standard knowledge. And I would say, in my opinion, those problems are usually better, because they are not similar to others, they are new, more interesting because of that. And they check one's thinking instead of knowledge. So I like that in problems, and I try to prepare more problems like that. I remember one of my problems related to some puzzles. It's called Bears and Juice. It was used in Conforces. And in short, the puzzle that I heard before inventing that problem was that there is some number of people and there are some number of barrels with wine or some containers with wine, and one wine is poisoned. And their goal is to find out which one is poisoned, and I think in the first puzzle it said that at least one of those guys must live. Okay, so all other ones can be killed, but they really want to know which barrel has poison. So we have some barrels with wine, and some people. And I think they had to do it in 2 days or 3 days. And the process is that in each day, each person chooses some barrels from which he drinks wine. And then after a few hours, let's say in the evening or in sleep, he dies if there was poison in some of barrels he drank. So if someone dies, we get to know whether there was, in his set, there was poisoned wine. And together with my friend, Mateusz Radecki, we managed to make it into a problem with some big constraints, and I guess it said something like find the minimum possible number of days in which they can drink, get to know where poison is. And also we made statement a bit more life-friendly, so instead of wine and poison, barrels by default contained juice and one barrel contained wine. And of course wine is bad because after a few hours you feel dizzy and you go to sleep. Because it isn't that cool to talk about, I don't know, death and being killed by poison in those problems. One more kind of known puzzle or mathematical problem that people in high school who are interested in maths get to know, like they can hear it from other people interested in maths, is that it's called princess problem or secretary problem. How many of you know about it? Does anybody? No? Maybe it's called different in your language. For example, in my language, I'm sure it's secretary problem, while I know Russians call it princess problem. So there's also a possibility it's called differently in English. So we know, let's call it a princess problem. There are n princesses, each with some beauty, and no two beauties are equal. And like, I am a prince, and those princesses will be presented to me one at a time. And at each moment, I should decide whether I'm okay with this princess, or I want to say no to her, and to discard her forever. We say that those princesses will be presented in some random order, so we can say that there will be random permutation. Let's say it's 2, 3, 5, 1, 4. And in each moment of time, I can't estimate how beautiful that princess is that is currently presented. So I see the first princess and I don't know that her beauty is 2. But once I move to the next princess, I can compare her to every previous princess. In other words, I can say which best princess this is in the order, in the prefix. And our goal is to maximize the probability of finding the best princess. So we don't care whether we will get princess with beauty 4 or beauty 3. We only want to maximize the probability of finding the best one. So it's kind of intuitive in that puzzle that we should skip some number of first princesses and then choose a princess the first princess that is better than all previous ones. It never makes sense to choose a princess that isn't better than all previous ones, because we only care about finding the best one. And like, there is no other possible strategy that could be optimal than choosing some length of prefix for which, even if we get to know this princess is better than all previous ones, then we choose it. For example, if there is a sequence of length 100, and it's 100, and we are at the third princess, even if we know that she is better than both previous ones, it doesn't say much about her. There is anyway probability, like, what is the probability that she's better than previous ones? 1 divided by 3. Okay? While the probability that she is the best in the whole sequence, even with that assumption, is very small. So without that assumption, it would be 1 divided by 100, while here we know that she's better than 2 of them. So I think there is no easy formula for that, but it's kind of intuitive that it's very possible that she's better than the 2, while it's unlikely that she's the best in the whole sequence. So the optimal strategy is to skip some prefix, and it turns out that it's okay to choose the length of that prefix in advance, because it doesn't matter for us whether some princesses in the prefix have permutation relatively to each other 1, 3, 2, 4, or maybe 4, 3, 2, 1. We only know that we had already some number of distinct princesses, and we don't care about that. So the only thing that we can use to make a choice is the length of prefix that we already considered. And in that math puzzle, it turns out that it's the best to skip the first 1 divided by 1 divided by e, the constant in math, e, a number that is roughly equal to 37% of n. Of winning, I don't remember that probability, but it's some constant. Like, I can tell you, it doesn't matter. So this was a puzzle, kind of puzzle, non-puzzle, and I made it into a problem that said, in advance, you also know value of each princess. Let's say we know exact beauty of each princess, so we are given a sequence of n integers, t1, t2, and so on, all up to 10 power 9. And we still, when we get a new princess, we can only compare her with previous ones. And now, instead of maximizing the probability of finding the best one, we want to maximize the expected value of princess we get. So we can use that sequence. For example, if the sequence will be something small, something small, something small, something very big, infinity, 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 it would be awesome to wait for a moment when we get a new princess and we know that there were already 3 worse ones previously. So in that case, we care that our princess should be one of some number of best ones. And this problem with constraints up to a few thousands was used in Topcoder, maybe even in Topcoder Open, I'm not sure. And it was solved by nobody during the contest. So, and tourists competed in that contest. And also, a solution is like 5 lines long. Like, the solution is extremely short. So by the way, I recommend you this problem. But what I tried to show is that you can take something interesting you know, and think about possible changes. Also, when you do it, there is a problem that you must be able to solve a problem. Okay, so I had a few problems in my life that I invented a problem in some moment, and then like thought about it for a few hours, couldn't solve it. And this is one of those problems that I invented once. It looked to me solvable. I was going back to this problem once a few weeks or months, and eventually I solved it like after maybe half a year, maybe a year. I don't know how many hours I spent on that one, maybe 15 hours in total. But I could do it because for me, I have some experience, and for me it looked like a solvable problem. And indeed it's solvable in n-square. Because, by the way, n-cubic solution is kind of easy. Some dynamic programming. Okay, so now we'll move to the testing part. When you are an author of problem and you want to check whether your solution is correct, this is something very easy. And it's the same with the situation when you're a participant in a contest and you want to check whether your solution is correct. For example, either you want to be sure because it's IOI style contests and there is no revealing, score isn't revealed. So you will submit a solution and only after the contest you will get to know whether it's correct or not. Similar thing is, for example, Code Forces and Topcoder, where there are only example tests during a contest. So you want to test your solution and get sure that it's correct in this case. Or in case of author, you have as much time as you want, and also you want to be sure that your solution is correct. So what we do in that case, we write a naive solution, some brute force, something likely exponential and extremely slow. In the best case, without using any assumptions. So if you are given a sequence of numbers, you want to check, you want to find some optimal subset, and it's very obvious for you that it's optimal to choose big numbers. So you made an observation that it's always optimal to sort numbers and choose some suffix of biggest numbers. To really test that solution, it's not only to write both the intended solution in linear time and n-square solution that is basically the same, just slower. You will indeed test the problem if you write an exponential solution that will check every of n power 2 power n subsets. And it works both in case you're a participant during a contest and when you're an author and you want to check whether your solution is correct. The difference is that an author doesn't have to hurry. It's a good thing because it decreases the chance that he will make a mistake while, for example, implementing that slow solution. And usually the most naive brute force is indeed something very simple. Of course, it happens that even any solution is hard. Sometimes it's impossible to iterate over all possibilities. For example, you have to construct a polygon with something. Even if polygon should have only 4 vertices, there are already so many polygons, possible polygons, that it might be impossible to iterate over all of them. So then you must think whether maybe it's enough to only consider coordinates up to 10. And then you must start thinking. But usually brute force is easy and is enough. And then you should only care about some big cases. So maybe your array is too small, maybe your program will be too slow for some case. But it's better to think only about those 2 cases than also about the correctness in general. Because this is the most dangerous part. Usually mistakes give you wrong answer because something is incorrect for at least one test, and usually small tests can detect that. But we're here talking about preparing problems. And what is the difference between wanting to check whether your solution is correct and being an author of a problem, preparing tests, and then wanting to check whether participant's solution is correct? What is the small difference that makes it so different and makes problems hard to test? Do you have an idea? Do you see a difference between those two scenarios? And the fact that we prepare tests in advance, that we must prepare, for example, 20 tests, it isn't an issue. Because you can also put many, for example, test case in one test. So testing on your machine, your own solution, it also can be done by preparing, for example, 10 test files. You just generate small random tests there. So what is the big difference, or small difference, that makes it so harder to prepare tests for a contest? Do you have idea for that? The difference is that when you wrote a solution, you thought that it's correct solution. You wrote something in a kind of honest and fair way, and you honestly want now to check whether it's correct. While during the contest, participant doesn't have to be honest and fair, doesn't have to just implement his solution, because his goal is to get accepted. So what he can do is he can try to squeeze some heuristic approach. This is one thing. And the second very important thing, that he can always write in his code, if the size of input is small, run brute force. For example, there is a sequence with numbers. If n is smaller than or equal to 10,000, then run n squared solution, because I'm sure it's correct. And if n is bigger, then run my not intended solution. I know it's incorrect, maybe as a participant. Maybe I even see some small test case where it fails, but it also works correctly for some cases. So if n is very big, then I will run this solution. Well, it's possible to put in one test, one file, 1,000 small test cases, and it usually completely checks correctness of your intended solution. It doesn't work during the contest. Because if all setters behave this way, if it's known that all setters anyway prepare only small test cases, then, and only a few big ones, because please notice that a random big test is often very weak. No matter, for example, if it's a tree and we try to generate it randomly, it usually has very small height. Okay, depth is very small. So, for example, any n squared solution that works fast if depths are small will work correct. So the thing is that we want to check time, and participants will try to, they don't have to prove their complexity. They will write some solution. And so it turns out that setter not only must check correctness with small tests, but the only tests that are important are big ones. Maybe not the only one, but the most important tests are big ones, because those indeed can't be cheated in a way, okay, I will write brute force here. So instead of just generating random small tests, now we have completely new part of preparing a problem, the most time-consuming one: prepare strong big tests. And now we will move to this part of the lecture. So we will see some examples. One problem. You are given a sequence of numbers and queries, each with one interval, and you want to find the sum of numbers in the interval. Okay, let's say I invented this problem. Of course, it's very well known, so it's best to use it in a contest, but we want to start with some not complicated example. What a setter must do? He must choose constraints. So it's okay to give n equal to 1. Like, it makes sense for a sequence to be this length. And there is linear solution, but we also, let's say, accept n log n. A very, very intuitive solution with constructing a tree, a binary tree, something very standard, and answering queries about intervals. So we want this solution to pass, and we can choose 1 million, but then time limit 1 second couldn't, it's possible that it wouldn't be enough, because maybe some solution would work in close to 1 second, so we would have to choose bigger time limit. Also, test files will be quite big, and if you have to upload them to the system, then it will also be slow for you. And there are no disadvantages of decreasing n, for example, to 200,000. This is, I think, my favorite constraint for n log n complexity. Sometimes it's 100,000, but then the n square solution works in basically 10 power 10, does this number of operations. And if we are able to cut the constant factor, for example, not really do n square operations, but n squared divided by, I don't know, 6, then this number becomes dangerously close to 1 billion, and computer is able to do 1 billion operations, like simple operations in, say, 1 second. So this is my favorite constraint. Oh, and we also should choose constraints for numbers in the sequence. And let's say we choose that everything has absolute value up to 1 billion. Now we will analyze this problem, and we will think what tests we should prepare. The most basic, of course, generator of tests is to just randomly, uniformly at random, generate all the numbers. Okay? So we choose, let's say, random n in the interval, allowed interval, and each number will be also random. Oh, and we have queries. So let's simply say that constraints for the number of queries q is the same as for n. So one possibility is that we generate everything at random. So each element will be a random element from this interval as well. And there will be queries. So of course, queries should satisfy the following. One is not greater than Li, Ri. So L and R are endpoints of interval in each query. So one solution, generate everything uniformly at random and only care about the fact that L shouldn't be bigger than R. Okay? If you just generate random number from interval 1 to n as L and as R, then it's possible that this one is bigger. Okay. One very easy improvement is that we shouldn't generate n and q uniformly at random in this interval, and that at least in some tests, we should choose maximum possible n and maximum possible q. So at least in some tests, likely in most of the tests, we choose n equal to max possible n, and q equal to max possible n, max possible q. Okay, this becomes reasonable. It also makes sense to, at least in some tests, choose big values of numbers. In this particular problem, I don't see a possible solution that would fail because of that. But solutions sometimes fail because of longs. This is one argument. Also, for completely random numbers q, the sum of n random numbers in this interval will likely be quite small. Because when numbers are some numbers are positive, some numbers are negative, so their sum shouldn't be close to n times the maximum possible value, because they use roughly the same number of negative and positive elements. So, and an interesting, not very useful fact is that I think that the expected value of the sum would be of complexity square root of n times max possible value. If you find the sum of n random values in interval minus billion billion, then I think this is the expected value of the sum. The expected value of the absolute value of the sum. But I think it's true. I'm not that sure. So in some tests, we choose most of the numbers to be big, for example, to be positive, or just in some tests, all of numbers, let them be equal to billion. And maybe in some tests, most of numbers should be very small. The next fact, when we very much care about the brute force solution, about solution in complexity n times q. So the complexity is n times q because for each of q queries, we iterate over numbers from L to R. But it won't be n operations. We iterate only between those two numbers. For random numbers, I think the distance between L and R is n divided by 2 or n divided by 3. But we don't care about that. We care that it isn't the pessimistic case for the slow solution. So what we should do is, at least in some tests, I usually say at least in some tests, because it's bad to make some assumption in all tests, because then you make tests weaker. Tests are strong if they are various, if they aren't similar to each other. If there is, each test has different properties. So at least in some tests, we try to choose small l and we try to choose big R. To make this solution maybe 2 times slower. Some other things can be done. So I see I think I see only 2 things that can be done, and one of them is easy to notice, and one of them is extremely hard to notice. Do you have idea for some other tests? So far we thought about the following things, and each thing means in some tests we try to get that. So random n, random q, maximum possible q, maximum possible n. Of course, it's good to have tests with both those constraints, equalities met at the same time. Some tests with big values, some with small values, some with small l and big R, and some with completely random values, completely random intervals. The hint is that we chose max q and max n. So what else can we choose in some other test? Very what? Small? Very low values? Yeah. So it's good to prepare some tests, in this case especially with n equal to 1 or 2. This is what we said? Okay. So it isn't that important to make q very small. Of course it doesn't hurt, but I don't see a possibility for some program to not work because q is small. Usually the bigger the number of queries is, the better. So in this problem, in almost all tests, no matter what is n, I would choose q as maximum possible value or very, very close to that. But yeah, it's very important to create tests with n equal to minimum possible n or close to that. So I would create tests with n equal to 1 or 2, maybe 3. Just to check some corner cases, maybe someone's solution, maybe someone's tree won't work for n equal to 1. It's possible. There is one more extremely tricky thing. Yes?
You could take all the numbers as 0.
Yes.
There is some division of stuff.
An idea is that in some test we can make all numbers equal to 0. It's also a good idea. It doesn't hurt to prepare such a test. I think it's very hard to write a program that wouldn't work on that test, but still it's something new, something different, and maybe in some other problem it will work. So while we say that all zeros don't, you can think that all zeros don't make sense here, but there are a lot of possible solutions. You can't guarantee that you see all possibilities. Here we talk about very straightforward problem, not complicated one. About something that you likely see all possible solutions and you have some intuition that all zeros they don't matter. Also, values of those elements don't matter, I guess. But maybe you won't predict something. And maybe other problem will be more complicated and then you will miss something. So it doesn't hurt to create some test. And one more very tricky thing is that it's good to create tests with, for example, n equal to, I don't remember the exact value, but not 10, 2 power 17. What is roughly equal to, I think so. Yeah, it should be true. So I would prepare, I'm sure in this problem, I would indeed prepare tests with n equal to 2 power 17 and n equal to 2 power 17 minus 1 and n equal to 2 power 17 plus 1. Why? I'm not sure I understand correctly. Can you speak louder?
Many times we use arrays, like global arrays, we just declare a constant in the code, which is sometimes 2 power 17 plus something.
Okay, so the idea was that sometimes people, when they declare arrays, they use some power of 2 as a constant. So it wasn't the reason, because maximum possible n is better to check those that kind of mistake. This test is better. Again, speak louder.
If someone chooses to solve it by segment, maybe some choose 4n to be the nodes, some choose 2n to be the nodes, maybe one or.
Okay, so the thing is that indeed one solution uses segment tree. So while one thing, easy thing is that this number is related to segment tree, so maybe it's good to give tests like that. But I will explain my reasoning. my reasoning is that sometimes arrays aren't global. For example, in my solution, I would indeed write something like int, let's say base of segment 3, base equal to 1. And it happens after reading n. While base is smaller equal n, base multiplied by 2. So the base of the segment tree, its size, must be power of 2 that is not smaller than n, or maybe strictly greater than n. If someone makes a mistake here and writes, for example, smaller than, while in fact he needed smaller than equal to, because, for example, a tree in 3 vertices are numbered, like leaves are numbered 0 through 2 power base minus 1. But in the statement, numbers are numbered 1 through n. So maybe he will make a mistake here, and he will choose too small base. So here, two most important tests, two very important tests for me would be n equal to that, and n equal to slightly more. And I'm not sure whether this one could be useful, but if I'm not sure about something, I also create such a test. And I understand that it's very hard to think about that as a setter. And as a setter, you aren't required to do that. A problem won't be bad if it turns out that you don't think about that test. This is just like making tests stronger. And thinking about this kind of strange things just makes them very, very strong. It's like kind of trying to make them perfect. So even if someone will implement a solution that fails for that test, and even if you forget about that, and even if people later see, oh, indeed, that test would fail him, like a contest, a problem wouldn't be a disaster or something. It's just some extremely particular case, and nobody should expect a setter to think about this. I just know about that because I prepared a lot of problems, so in total I spent a lot of time thinking about tests in various problems. So in some moment I got that idea. Unfortunately, I'm not aware about any materials in the internet about creating strong tests. Maybe in some moment I will start writing such blogs or something, but it's hard to cover many things. Here, for I don't know how long, I talked only about one particular problem. About one particular problem with some type of queries, something. So it's very small part of possible problems, possible tests, and so on. So the approach should be more that you should understand what good tests should be, and then you should know how to analyze a problem you're preparing, and then about what maybe you should think. Nobody will tell you how exactly tests for your problem will look like, because your problem is something new, and likely you must design tests for this problem without using tests or using some instruction for other problem. In this problem, it's also possible that there is second type of queries that change some value, but I don't see anything particular about that query. There is nothing interesting I see here. But of course, if there are two types of queries. So in this case, there is query give sum of interval and change value of one element. Then you should create tests where most of queries are give value of interval, sum of interval, and there should be tests when most tests are change something. Because maybe someone's solution works slowly only for one type of tests. The final thing, there should be tests where L is equal to 1, and there should be tests where R is equal to N. Okay, to just cover everything. Because maybe someone doesn't do something correctly for N. Maybe. Do you have questions so far? If not, we will move to the next example problem.
You said like four tests of one kind, so maybe someone can implement two implementations.
Maybe someone will have two implementations?
One for a more one for a less one. They can do either.
Yes, it's possible that someone will detect from the type of tests. It's possible that someone will read the whole input and then his program will check whether there are more queries or the first type or the second type. And maybe he will run different algorithm for both cases. So it isn't true that two tests are enough. One with almost q queries of the first type and only a few of the second type, and one the other way around. You should also have tests with similar number of queries of both types. Because all the time I'm saying, when we have a new idea, we don't do it in all the tests. We just create a new test. Okay. Question is how to choose time limit, right? And memory limit. So memory limit is almost all the time not a concern, because memory limit is some default big value, usually 256 or 1 gigabyte, and in 99% of time we don't care, because anything will pass. Maybe sometimes you must increase it. Maybe sometimes you want some solution not to pass, and the only thing that you can do it is to decrease the memory limit. There are some programs where it's all about the memory limit. For example, the problem says the memory limit is only 1 megabyte, and maybe it requires completely new solution because of that. But you should assume that usually you don't care about memory limit. While time limit, it depends on the contest a bit. For example, in a short contest, so some contests are long. And by long, I don't mean 5 hours. I mean, for example, 2 days or 10 days in Couchchef long contest. In short contest, it's very important that when someone implements the intended solution, he should get accepted. Otherwise, if he has to squeeze his solution, he has to make it a bit faster. It's a bit, maybe not discouraging, but it makes his situation a lot worse. So we always try to aim in the situation where the intended solution passes test. So this is the most important thing. The intended solution should pass. Of course, if it's written in a very bad way, if it's 100 times slower than the intended solution implemented by author, then it's participant's fault. But generally, it's kind of a golden rule that in short contests, intended solutions should safely pass. If you want to have some particular rule, particular multiplier, is that my advice is to choose time limit as 3 times intended solution. For example, if your intended solution works in 1.5 seconds in the worst possible case, like you already created tests, because of course time limit can be chosen at the end, after creating tests. You create a test, then you see that the worst time of your solution is 1.5, then it seems reasonable to choose 4.5 as a time limit, and of course you can round that. It's worse to round it down because like time limit, this formula means that there should be like a participant's program can be 3 times slower, up to 3 times slower. So by rounding it down to 4, you change that. So I would round it in this case to 5 seconds. Of course, maybe in some problem the stupid solution is only a bit slower than the intended solution. So maybe you must try to be a bit tighter with time limit, and it's possible that setting 4 seconds is better. If, for example, the slow solution that you implemented works in 5 or 6 seconds, then it doesn't mean that you should choose time limit equal to 4 seconds. Instead, it means that you should change constraints. You should change tests or something. If you set time limit as 4 seconds and you are aware of a stupid solution that works a bit slower, then likely someone will squeeze it into the time limit. It isn't guaranteed that your implementation is the fastest possible one. So one thing is that there should be difference between time limit and running time of your solution. The second thing is that there should be difference between time limit and the running time of the fastest of your stupid solution. And I never thought about formula for that. I think it's reasonable to assume that slow solutions should be, let's say, 4 or 5 times slower than time limit. But it depends on the problem so much that don't treat it as a constant. So this was about short contest, and in long contest like CodeChef, there is more time. So there is also more time for squeezing solution, no matter whether your solution is correct or stupid, like intended or stupid. So there, I would be fine with 2 times intended solution. Because if participant found intended solution, he implemented it was too slow, a bit too slow, then he has time. He can improve that. But when you start, there is always someone more experienced than you in the set of people working on a problem, so you shouldn't be afraid that much. And when you start, someone else will help you. So even if a tester only had experience with like 5 contests already, not 100 contests, anyway, he will know something, so he will help you. So you shouldn't be that afraid that you don't know the constant for that formula, so you can't prepare a problem. Okay, so now let's move to the next problem. The next problem is similar. So we have a sequence of numbers. We can have the same constraints. I will only remove this. And the difference is now, instead of finding the sum of numbers in the interval, we find the maximum value in the interval. Now, apart from things that we already talked about, that there should be maximum n, there should be minimum n, and being power of 2 or close to that, now values are very important. This is one thing, and the second thing is that now not necessarily big intervals are the best. Because if you only choose random intervals, they're usually long, then maybe in the whole sequence of numbers, when you care about maximum of some long segment, then likely only a few numbers in the whole sequence matter and can be a solution for some query, an answer to some query. Because if you have a sequence and you ask about some long interval, small intervals in the middle don't matter, right? So maybe a participant will invent some strange solution where he only updates and he only checks as an answer some big values. For example, the biggest 100 in the sequence. So one observation is that we should make some queries to be smaller. Maybe it's reasonable to make a lot of queries with size of interval like 2000, because then still brute force solution in complexity q times that won't pass. If you think that it will pass, then you should increase that value that you think about, maybe 10,000. This is one thing. And the second thing is that choosing values randomly isn't good anymore. You should think about some particular patterns. For example, it makes sense to make in one test values that are increasing. And it makes sense, even more sense, to make it increasing with some small shifts. So now generally values increase, but not so regularly. So the answer isn't always the last number in the interval. You can also, a few random numbers, elements, you can shift by big value. And it would be better to shift some numbers by random value up, because then those few numbers that you shifted up would start to matter, and other values could be like discarded in the participant solution. So I think it's better to shift some values, to decrease them like hugely. So there will be values around, let's say, 10 power 8 here, and suddenly there is number that is about 1000. To make test a bit more complicated. It's also some idea to make values roughly decreasing in some test. It makes sense to make values first decreasing, then increasing. You just should think about some ideas, some patterns. All tests so far, all types of tests so far, have one bad property, that when you ask about some interval, likely the answer is either close to the beginning or close to the end. In all increasing one, decreasing one, and so on. So maybe it's also reasonable to prepare a test where first values increase and then decrease. Of course, there should be tests with completely random values. I would also, this is more advanced idea, I'd also create a generator that for some chosen by me value k splits the sequence of n numbers into k intervals of, let's say, similar length. And I try to repeat some pattern in each interval. Let's say that I chose the pattern with first increase, then decrease. But by repeating, I don't mean that numbers here and here are the same. I just mean that pattern is the same. So maybe here maximum value will be 50, and here it will be 52, while here it will be 48. There should be just similar. It's just some completely new type of test where any heuristic approach should not work, and it makes this test better because it's something new. And like, I chose this exact test because it indeed has a lot of good properties. Because in this problem there can be solution in something like linear time times square root of something. It's possible. So, and this is test kind of trying to be the worst possible scenario for this solution. But we won't go deep into that. It's just a good test because it's complicated. And I would choose various possible values of k. In some tests, In some tests I would choose k equal to 15. In some it would be 10,000. In some it would be close to square root of n. So this shows that even a quite simple problem possibly has complicated tests. Now we'll move to trees for a moment. So there are a lot of problems about trees, and it's very possible that if you will want to prepare some problems, you will invent something on trees. So possibly in that problem there will be some queries, some values, and even without caring about that, you should, maybe it will be good to make queries random, but it depends on your problem. But in general, what matters is how your tree looks like. And there are so many types of trees. So there is a tree that is a line. So even for maximum possible n, it can be line of length maximum possible n. There is a star. There is a double star. There is a perfect binary tree. And maybe not perfect binary tree. There is completely random tree that can be generated in two ways. One way is that you start with one vertex, and each new vertex you add to random vertex so far. For example, a tree could be like that. And now we create a new vertex and we add it to a random of previous ones. The expected length, depth of this tree would be logarithm of n, by the way. This is one way. Some other possibility to create trees is to imagine n vertices, a graph with n vertices and 0 edges, and in a loop, as long as not everything is connected, choose two random vertices and connect them if they aren't already connected, possibly not directly. For example, I add some edges. Now if I randomly choose this vertex and this vertex, I shouldn't connect them because they are already in one connected component. So I can use find an union to do that, and eventually I will get some tree. In this tree also depth would be logarithm of n, what is quite hard to analyze. And one more way to generate kind of random trees is to use what is called proofer sequences of or codes. P-R-U-F-E-R. You can read about it later. So as you can see, there are many possible types of trees. But of course, there are more of them. And it also makes sense to combine those ideas. For example, one test that I always include in my problems is about half of vertices made into a line and then a star at the end. Or maybe not at the end, maybe somewhere in the middle because a line goes on. Okay. Star means that there are many vertices connected to one vertex. Maybe for some solution this exact tree will make this solution to be indeed n square indeed of linear time. And one more advice about trees is that instead of just giving a line that can be easily dealt with in a solution, because when someone gets time limit exceeded, he can try to hack tests. He can try to be a cheater, kind of cheater. It's allowed, okay? So it's setter's job to fight with that. So maybe he will try to check if the tree that is given in the input is indeed just a line. So maybe it's good to just add a few single edges, extra edges. And the same goes true for other other types. So this is a tree. Let's very shortly talk about graphs in general, what is strictly harder topic. So you can generate a random graph just by, for each pair of vertices, just by generating random edges, right? Possibly you want to make this graph connected, so then after generating random edges, you just connect all connected components that you have in this moment. You must connect with, so you have three connected components and you connect them then at the end in any way to make everything connect. Maybe you will make first a tree, big or small, and now each vertex can be replaced with some small, or maybe not small, random graph. So maybe you will want to make some random graph, not necessarily a tree, then connect it to the next small random graph, and so on, and to make that it a line of graphs, and maybe a star of graphs. And well, there are many ways to create graphs. One example of problem where I had to think about one particular, not one, about some particular types of graphs is problem that is called bear and finding criminals. It's about, the story was about some bear criminal detector, and in that problem the input contained a graph, not necessarily a tree, and what mattered for me a lot was that that graph should have a big diameter, because the complexity of two-slope solution was, instead of something like n square, it was, I think, n constraints were maybe n up to 300. I don't remember. So the complexity was of two-slope solution was n square times diameter square. So I wanted to achieve big diameter. And what I did, the strongest type of tests there, behaving good against this solution, and at the same time hard to be hacked in any way, because I also could just create a line, just a tree that is a line, and it would have maximum possible diameter. But the thing is that it could be easily avoided, like it could be easily checked whether it's a line. So my best tests there were constructed in the following way. I made a big cycle where each vertex of this cycle is a small random graph. Like kind of, usually those graphs had like 6 vertices each. And something like 10 edges, for example. Not necessarily those numbers, of course, are created various ones. But this was a very good test, because indeed in that story where something had to be computed and we cared about optimal solution, and when a problem asks about optimal solution, then it's very hard to prepare tests, because maybe even if program is incorrect, maybe it will manage to find the optimal solution. And in that particular problem, this test turned out to be very strong. So the thing is that graphs and trees problems are hard to prepare, but basically you should base on some types of trees, some types of generating trees, of generating graphs, and maybe in your problem there is some particular solution like this one, and then you want to create a test designed especially against this solution. So in this case, I knew I must prepare a lot of tests with big diameter. So I thought about not 3 tests with that, and I thought about big cycle. And to make it more reasonable, to be harder to find the optimal solution, I added those graphs instead of vertices here. So fortunately we are done with graphs and trees, I think. So now the question for you is whether you want to hear a bit more about inventing problems or about testing them, creating tests for them. So maybe hands up who prefers creating problems and talking about that, and hands up who, okay, so we know everything now. Okay, so creating problems.
Can you discuss about problems involving real numbers?
Involving what?
Real numbers, real values.
The question was, can I
Nice solutions or some. How do you prepare tests for those type of
Okay. So, first there was a question about real values. To prepare a problem that in which solutions possibly have precision errors, you must understand how precision works. It's good to understand how it works in a machine, and it's exactly the same skill that is required to solve a problem about precision, and understanding that your solution will work. So it isn't, like, I don't see how it is more a skill for a problem setter than for a contestant. So I still can talk a bit about that. It's possible to prove some precision. So, for example, if we read some number from the input, say x, then we can assume that the precision number of how this number is stored in the machine is up to some epsilon. And epsilon depends on the data type. For example, for for double type, it can be maybe 10 power minus 15, but you can check that by checking how many bits in double. You can check in the internet how many bits are there to store the number, because double is stored in 2 parts. One part stores maybe. Okay. Each number is stored in machine as a times 2 power b. Let's assume that each number is stored like that, and double consists of, let's say, 55 bits. I don't remember exactly. I think it's 50 something. Where, let's say, 45 bits are to store A, and some number is to store B. And it gives us some limitation. The number of bits that store A means how good precision we have, and the number of bits here means how big number can be. And for example, 45 bits of precision would mean that we should expect error of at most 2 power minus 45. So we can assume that x taken from the input, or just simply computed. So for example, we say x equal to 1.2, then we should assume that it starts with at most this error. When we add 2 numbers that are of the same sign, so for example both of them are positive, then the answer machine works in that way that the answer will also have at most this error. But if you add two numbers of opposite signs, for example, one is minus, maybe let's see an example. We add 50 plus 60. And the relative error of this one is at most 10 power minus 9, and the same for this one. Relative error equal to k for a number a, means that error is at most absolute value of a times k. Okay? For example, if number is equal to 1000 and relative error is 10 power minus 6, it means that exact error, or in other words, absolute error, is equal to 10 power minus 3. Relative error means, am I right? Yes. Relative error means how big error is compared to the number. So in this case, relative error equal to, and also here, we said that this is also relative error. Everything is done with relative errors. So if we add two numbers of the same sign, we should expect that error here is at most, exact error, absolute error, is at most 50 times 10 power minus 9. Error here is at most 60 times that. So total error is at most 50 plus 60 times previous one. So if we say that this is equal to 110, we can say that in this answer, this is the limitation. We proved that limitation for the answer. So relative error is still 10 minus 9. The problem is when we add two numbers of opposite signs. For example, minus 50 and 51. The answer will be 1, while error here can be up to 50 times 10 power minus 9. Here error can be 51 times 10 power minus 9. So the total error can be up to 101 times the previous epsilon. When we add two numbers of opposite signs, we can say that now the relative error is the same as previously, 10 power minus 9, because we got this limitation for error now. So it isn't equal to 1 times 10 power minus 1. Now error became much bigger. Other intuition behind that is that if you add number minus 50 with number 50, you should get 0. But even if one of those are shifted a bit, for example, it's stored in computer as after comma something small, then the answer becomes that something small instead of 0. And it means that relative error is huge. Like it isn't even defined, because relative error is error divided by number that should be presented here. So perfectly, if number should be 0, we want to get 0. And here, for example, if we now multiply this number by 10 power 9 by billion, because I don't know, the statement said that we should print the output multiplied by that. Now we would get this multiplied by 1 billion, it would be like 10,000. So we got 50 minus 50 is equal to 0 times 1 billion is equal to 10,000. So this is some way of proving something formally. It doesn't happen that all setters do that. If you understand precision well, you don't have to think about that. Like, for me, it's obvious that I can add numbers, for example, of the same sign. I also quite understand how multiplying works. So multiplying and division is, of course, a bit more dangerous than adding and subtracting. Something also more dangerous is square root, because like, it's more complicated operation. But what you should think is often whether if something in the input will be shifted by small value, by some epsilon. And this means, it's a bit similar to situation if some of early operations will give slightly wrong result, for example, that. So if something in the input will be shifted slightly, then will the answer change much? Usually it doesn't. And I will use the same argument. When you start with setting problems, you should hope that at least coordinator, tester, or whoever will understand possible issues here. So it's some advertisement for CodeChef, because if you propose problems for CodeChef, I'm currently coordinator, so you don't have to care much about precision error. And like, eventually you will be better participants, and you will also understand this topic more, and you will also be better problem setter. This is how it works. But if you're afraid about your problem, if you don't understand whether something will work, if you have some doubts, then of course it's safer not to use a problem, or maybe wait with that. Maybe once you will be able to solve it or to see possible issues. Okay, and the other question was how to design tests for some square root decomposition. I think it was the question. I'm not sure whether I should answer that, because most of you voted for talking about creating problems instead of testing them. So I think I shouldn't talk about that, and maybe you can ask me after the lecture. So something more about creating problems will be that some problems should be discarded, shouldn't be used. I will give you two examples of two problems that I decided not to use recently from my ideas. Okay. One thing was that I was on YouTube and I was listening to music. It was during some lecture here, so I wasn't listening too well. And after each song, there is another song, right? Like there is autoplay in YouTube. And in some moment, I got a song that I already had like minutes ago. So I got the following idea. For each song, we know which song will be next. And now we wonder what song we should choose. Also, possibly each song has some length. What song we should choose and what will be the answer, so length, to maximize time we will listen to different songs. Also some possible version, a bit harder, is that maybe we aren't that lazy, and in one moment or in k moments we can change a song. So one song ends, possibly we see that the next song will be the same as something previous, so maybe we can now change a song. In graph interpretation is that we have a directed graph where each vertex goes to exactly one other vertex. And all those types of graphs can be represented in some particular form. In Polish it's called medusa, medus. I'm not sure whether it exists in English. Have you heard about word medus? So there's a cycle and there are trees. So there are some trees and each of them goes to a cycle, and this is the only type of possible connected component in this graph, this directed graph. And then if we can't change a song, then it's enough to just consider going from some leaf of a tree, and then the answer will be the length of path from leaf to root plus the length of cycle. So for each connected component we should just consider the length of cycle plus the longest possible, the maximum of distances from leaves of trees to roots. So it looks like a reasonable problem, and my only issue, and the only issue I saw was that I think that it's very easy to invent this problem. That I saw already a lot of problems about this kind of graphs, and so here I asked just about the longest path. I just thought it isn't that cool for me, at least I don't see it to being very cool, maybe because I don't like graph problems, and at the same time I'm afraid this is known. So I didn't even bother much with version about changing at most k times. Like I started thinking about that and I just didn't like a problem much. So when I'm a setter, I'm allowed to think whether I like a problem. So when you take a random problem from my set of created problems so far, you are much more likely to get some topic, of course. I'm not even able to say exactly what topics those can be. I think that I don't like graphs and strings, for example, but I don't like graphs, so I didn't enjoy this problem that much. So this is one example. And the second example, so this I discarded because I think it's known. And the other example I discarded because I think it's boring. And like, for sure it isn't well known, but solution isn't interesting. It's just implementation. So I was thinking about Battleships game. This is a game where you have a grid and you have some ships. And your opponent tries to guess where your ships are. And my idea was that to do something with that Battleships game, my exact idea was that we know some state of the grid. For example, we know what places we already hit our opponent. For example, we know that we already killed 2 complete ships, and we started killing some other. We know where we tried to hit, but it was an empty cell. We know the exact rules. So, for example, we know the number of battleships of each length, whatever is needed. And now I thought about the following versions. One, in how many ways we can put ships so everything is okay? How many ways are there to put ships here? The second way is there a cell that contains a ship for sure? So can we guarantee that our next guess will be correct? And I like this problem a bit because there are some possible wrong approaches, something greedy-ish, and I indeed found counterexamples. So I saw some solutions that won't work for some tests. And it's always cool to it's cool to make people think that they have a solution while solution is something more complicated, harder. So they shouldn't think again. But on the other hand, generally this solution is just implementation. You can either implement something completely naive and power the number of cells in the grid, or you can do complicated dynamic programming going from left to right and remembering the state of, let's say, the last column processed so far. And we also remember what ships we used so far. And then we can move to the right and we can make this approach to be complexity to power the number of rows times n times m and maybe times the number of ships or something. So I was quite sure this is a new problem, at least one version of what I thought. The one with whether there is a cell with that for sure contains the part of a ship. I think it was original, but this is just implementation. For me, there was no thinking in this problem. So I didn't use this problem. So as you can see, here I didn't use because I thought it's well known. Here I didn't use because I didn't like the solution. So those were it was about like, removing problems, not using them. And now I will tell you one more way to invent a problem together with some story, some actual story about a problem that is a contest that lasts right now. So there is a contest now, in CodeChef, of course, long contest, and there is a problem digit multiplication or something like that. I think problem name is multiplication program. So you will have some advantage because you will know story about that problem. So I will first describe this problem. Or maybe, okay, I will start with story. So how this problem was created. I was on a camp, ACM ICPC preparing camp, and we just had those 5-hour-long training from some old contests. This is how you train for ACM. And one training was apparently prepared by some university, some country, where when they gave problems to others, okay, those problems are from OpenCap contest. It's a series of contests that uses just each university country competing in OpenCap once in a time gives their own problems to that contest. For example, let's say if India wanted to take part in OpenCap, but maybe it would be hard because of time zones, for example. So maybe there is a snack down contest in India, and after finals, organizers would choose some set of 10 problems, for example, and give it to OpenCap. And it would be soon used in some OpenCap contest. So this is kind of like just sharing. It's also impossible in this case because Snackdown is international contest, so anyway many teams know problems. While problems in OpenCap should usually be from some problems that were known only to some particular country university. So I don't remember from what country or university that contest was, maybe from Japan, but anyway, apparently organizers didn't know English very well and statements were written in very bad way. Okay? We had to guess some parts of the statement. There were so many mistakes and sometimes it was hard to understand. And in one problem, the statement was that you have to choose some sequence of moves. You must kind of implement a machine that will be able to multiply two numbers. So we have two numbers. We know that they have some digits. And let's say that the memory of the computer that we consider has many cells numbered 0, 1, 2, 3, and so on. And let's say that in first, say, four cells, one number is written. In the next 4 cells, second number is written. And the goal of your sequence of moves that you will print is to multiply those two numbers and put the result of multiplication in the next 7 cells. To do that, what you should do? You should choose a function f. Let's say the f should take 2 digits, a and b, and should return something. So in the output you should print 10 times 10 values. For each number a and b, from 0 to 9, you should choose what should be the result of function f. So you choose a function, and in each move you choose three cells. For example, second one, some cell, and some cell. And that machine that we consider computes function f from value here and value here, and the result is printed here. So, for example, it's quite maybe reasonable to say that function f is just a plus b modulo 10. This is function that we can choose. And then we are able to add 2 digits and to write their result, the result of addition, in some other cell. And then if there will be 4 there, 8 here, and we make a move on these 2 cells and apply it here, 2 will be written in this cell. Of course, please note that the only thing that is given in the input, there is no input. Oh. In this program, there is no input. We should just choose some function f with 10 square digits and print some moves, some limited number of moves. There was some limit. And your output will be correct, will be accepted, only if for each possible numbers here, for all possible numbers here, your sequence of moves indeed will put the result of multiplication in the next cells. So this was the problem. It appeared to be quite hard, but we saw many teams in the leaderboard to solve it. Because on that camp, we were like 10 Polish teams maybe, but we saw it was virtual participation. So we saw results of teams who participated previously, earlier. We saw that this problem should be easy. But it's so hard. It's kind of intuitive to make this function. And then, for example, we can take the last digit of the first number, the last digit of the second number, and write it in the correct place. But it's very hard to think what happens next. Not only we must care about that maybe multiplying, sorry. I think it's more intuitive to think about multiplication. This is what I meant, sorry. So, and the same happens for addition. So for we can multiply 2 numbers, write it here. But what next? We'll multiply numbers, let's say 7 and 7. We'll get 9 here. In some way, we must know that we should also there is also 4, because 7 times 7 is 9 plus 40. So we should add 4 in the next cell. But how to do it with one function? We can also decide that this function will return a times b divided by 10, let's say, to extract that other digit. But then, how to get this digit? So it's intuitive to think about multiplication or about addition, because multiplication is just like addition many times. And I think in example explanation or something in this problem you will see addition. But anyway, we didn't see a solution, but eventually, like, I started this story by saying that statement wasn't written in a good way. Eventually, one team managed to guess a correct solution. And let me first say that there was no sample example output and input in this problem, because there is no input. Output would be huge, because it would just contain the whole sequence of moves, and also the output would be the whole solution. So there was no example input output. So it was quite hard to guess that we don't understand the problem in a good way, because in fact it turned out that an author meant that in each move we can choose a new function f. And now the problem was very easy, because we could first take, let's say, those two cells, choose a function a times b modulo 10, and make a move that takes those two cells and prints as a result here. Then in the next move we can choose the other function that returns a multiplied by b divided by 10 to write the next digit, 4, in the previous cell. Then of course it still won't be that easy, because when we'll care about some other one digit from here, one digit from here, we'll multiply them. We don't just write result here, we must add it to the current value. Exactly how multiplication works. But what we can do is we can make a move and remember result in some other cell for a moment, and then add those two cells. So make a new move. This time it will be addition, a plus b modulo 10, and take a result of addition, and also care whether, so with the third type of function that we will use will be a plus b modulo 10, and the last type will be a plus b divided by 10, because when we add two digits, like 4 and 9, let's say, we also have to know that it's not only 3, it's 13. So we can also add 1 in one more place. So for about 3-4 hours in a contest, many teams, and there are some strong teams in Poland, tried to solve the version with only one function. None of us wasn't even close. And eventually one team managed to guess the correct statement, based on the fact that, indeed, the leaderboard said that this problem was easy. So he announced to everyone what the correct statement is. Everybody solved that. And later, after that contest, I spent a lot of time, and I managed to solve the first version of this problem. And this is exactly how this problem was created. So one other way to create a problem is to misunderstand an existing one. So of course, it's quite hard way, because usually you understand a problem correctly, but it sometimes happens. Also, it's possible that it already happened to you that you were solving a problem, and after implementing a solution you realize that you didn't notice some assumption or something. So sometimes in that case it also means that in some way you invented some problem. And it's up to you to think whether it makes sense to you to sit in a contest. So in my opinion it made sense to use this one in a contest, and I recommend you to think about it. But I think it will be quite hard, and right now I think there is still 0 accepted solutions, but the contest started hours ago, so maybe it will change. in a few hours, maybe by someone of you. And with this problem, I will end my lecture unless you have some questions. Okay, thank you. Then if you have more questions, if you will think about more questions later, just ask me. Thanks.